So this is the second video for the 2019 higher triple paper for year 10. So let's have a look at the question here. Experiment. There's a 16 ohm, 12 ohm and a 6 ohm resistor all connected below. So you can see that you've got the 12 ohms and 6 ohms in parallel. So we're going to have to use an equation to calculate that. And then you've got this one in series. So let's do that. Let's calculate that and then we'll know. It's just a case of adding them up then. So I've done that. So I've done 1 over RT total, RT, equals this from the front of the equation. So you can see 1 over 12 plus 1 over 6 comes to 0.25. So R equals 1 over the answer that we just got, which is 4 ohms. So I got a maximum of 4 ohms here. And then because that's kind of collapsed now, the whole thing is 4 ohms. It's almost like in series. So 4 plus 16 is going to give me 20 ohms. Okay, so a 4-mark question coming up. So there's going to be 2 equations. A brand new battery is used. Manufacturer states that this can transfer a maximum of 75.6 kilojoules of energy. So we've got energy here, so I'm going to have to use that in an equation. The current from the battery is measured as 1.5 amps. So I've got a current. Use the equation P equals current squared times resistance to calculate the time in minutes. So once we found seconds, we've got to convert it into minutes. The battery will last. So what I've done is taken my current. So I'm going to use this first, power. I'm going to find my power in order to find my, because I know my energy from there. I don't know my power, so I've got to calculate my power to get my time down here. So in order to do that, I need to use this equation. So 1.5 squared is my current times my 20 resistance. It's going to give me 45 watts. And all the while I'm checking my units so I don't have to convert to anything. So it's going to be coming out to 45 watts. Now I know my power, I can rearrange this equation for time. So T is going to be equal to energy over the power that I've just solved for, and that comes out to 1680 seconds. To get that into minutes now, I simply divide by 60. So I've done it there, comes out 28 minutes. 6-mark question then on earthquakes. Compare the seismic traces obtained at A, B, and C. So station A, station B, station C. So we can already see A and B are getting deflected there. Station C goes straight through. So let's talk about station A. We'll detect both seismic waves as they are able to travel through the solid mantle. The P wave will arrive first, then the S wave. S waves travel slower than P waves. This results in a small time lag between the detection of the P and S waves. Station B is pretty much identical apart from the fact that they get these signals a bit later. So station B will detect the waves in the same order as station A. However, the P waves will be detected at slightly later time than station A, because station B is further away from the earthquake. Compared to station A, there will be a bigger time lag between the 2 waves because of the increased time or increased distance it has to travel. And then for station C, we can see that it's right below. So this will only detect the P waves. The reason for that is that the S waves cannot travel through, as they will only detect P waves, as the S waves, I should put there, cannot travel through a liquid. It would be the last station to detect the earthquake because it's the furthest away. And then we can also add on the end there that amplitude is the amplitude of the detected waves will be smaller. They decrease as the distance of the earthquake increases. Okay, so let's have a look at the last bit this then. S waves are transverse waves and P waves are longitudinal. What's the difference between them? Nice, easy 2 marks here. Transverse waves, vibrations are 90 degrees or right angles to the direction of the wave. And longitudinal, they move in the same direction as wave travel. So they're parallel to the direction of wave travel. So 2 marks, essential 2 marks there. Okay, electromagnetism. Let's have a look. So the first one is all about using Fleming's left-hand rule. And we kind of have to describe for 3 marks what we're doing. So first of all, I've said, and I've drawn, it's really hard to show on paper and obviously in this video, the directions. So the first thing I'm going to say is that the first finger is going to represent from the north to south. So you need to point your finger from north to south. Once you've got your first finger going in that direction, your thumb is going to move upwards. And the current, well, actually, we've got to do the current this way. You can see that the current is going around. There's little arrows, directional arrows. So now we know that our middle finger has to point, oops, sorry, didn't want to do that. Has to point this way, so it goes round like that. Therefore, your thumb is going to be up. And that's why the wire moves up there. So tried to put that the best I could. I mean, even the mark scheme's a little bit fluffy on this. I don't really think they thought about the question before. So do your best that you can there in describing Fleming's left-hand rule. We've got 2 graphs then. One's showing mass against force and the other one's force against current. So we've got one variable that's the same. So this is now moved to there. And we're going to need that in the next question because the next question is asking us to find the force at 4 grams and therefore the current at 4 grams. So first of all, I'm going to find the force at 4 grams. So you go to 4, go back, and then we see that it's 40 times 10 to the minus 3. And then once we've found, so we're going to write that in, 40 times 10 to the minus 3. And now we can find the current once I found my force. 40 back to 1.8, I think it is. Is it 1.8? Yes. So describe the relationship between current and force. Current increases, force increases at the steady rate. So it's directly proportional. You can see that from the straight lines. So as one doubles, the other one doubles as well. Okay, so this one, so I don't think you do this in year 10 maths. I do think you've done it probably in chemistry maybe, where you've got the equation for a gradient. And in maths you will do this in year 11. It's unfortunate it pops up now in year 10. So what it's saying is the y-axis is equal to the gradient, which is m, and then your x-axis plus your intersect, which is c. Not a lot of people got this question right, so not a lot of investment in this. A lot of students see this and think, oh, I'll just move on. But I can describe what's going on now. So you have to compare this with this equation that you can find in the front of your booklets. And we can say, so from these graphs, what is going on. So your y-axis is going to represent your force, and that's obviously represented by there. So your y-axis. Your x is your current, which we use the letter I, so that's why I've circled that. There is no intersect because you've got nothing after, there's not plus anything. And we know there is no intersect anyway because it travels back to 0 there. So there's not going to be any intersect. So what we're left with now is that m is going to equal b and the length. So the gradient, which is m, is b times l. Okay, so let's have a look what's next. So the length of the wire contains magnetic field B. So B represents your magnetic field strength. Oh, I didn't want to do that. And it's the wire is 5 centimeters. Use information from graph to calculate the magnetic field strength. So what we're going to do is use y over x to get our gradient. And then once we've got our gradient, which is m, we can use that to calculate the magnetic field strength. So from the graph, I used 90 over 4. So I've just gone, where have I gone? I've gone, I don't know what I've done here. Hang on. Yeah, 90 over 4. So I've got a change in y over the change in x there. And that gives me a gradient of 22.5 times 10 to the minus 3. And now I'm going to use that gradient to calculate my magnetic field strength. So the gradient now over the length of the wire, 5 centimeters, is going to give me 0.45. And that's that. Okay, a couple more questions to go. So we got an experiment carried out here. Abigail concludes that the input voltage increases and the transformer becomes less efficient. So I've said that I agree with Abigail because you can see, so what we've got is your input there, that's your voltage, and then your output voltage is obviously lower at this point, so it's not 100% efficient at all. But it is till this point, because they follow the same path, and then you can see that they separate. So I've said the transformer is 100% efficient up till around 46 volts. Be careful of the scale there. Then output becomes less, so I do agree. Use an equation from page 2 to calculate the current supplied. So I equals P over V in this case. I think the equation they give you is P equals V times I in the start of the book, but I've just rearranged that. So that's going to give me the power of 180, which is where input power goes. And that's going to be over 100, which is there. Okay. And that's going to give me 1.8 amps for 2 marks. Explain the purpose of laminations in the soft iron core in the transformer. So you're going to get less heat loss because of it. It's going to prevent overheating in that case because there's less heat loss, and then more efficient, we can say as well. Now it's worth 2 marks. I've given you 3 options there. So a nice little memory question there. Explain the advantages of using high voltages. And this is a crossover between double as well. High voltages results in low current, so less energy losses heat, more efficient transmission, which is excellent for everyone. Okay, last question then in this monster paper. So this is a pressure question. We've got some temperatures here, and we've got some trapped air, the volume of trapped air there. You can see it's increasing with temperature. This is something you're going to have to put on a graph, so you're going to have to put your own scales. So you're going to get 1 mark for your scales, you're going to get 1 mark for your plotting, and then you're going to get 1 mark for your nice line of best fit there for 3 marks. And then explain using your graph whether the students can take the volume reading from a syringe at 100 degrees. Well, let's have a look where 100 degrees is. So there's 100 degrees, look, right there. And let's go up, and it's going to be around about, I don't know, nearly 26 centimeters cubed. Tricky question, because now you have to recognize that the syringe only goes up to 25 centimeters cubed. So they do try and trick you on these questions. So I'm going to say it can't be used because the syringe, it will exceed the maximum volume of the syringe there. Last question. I mean, this last question is a stinker. I've even wrote stinker there. But let's do the 2 easier ones first, which is memory and recall. Explain how, if at all, density of trapped air changes as it is heated. Actually, this is interpretation, this one. So we can say the volume increases as the separation of molecules increase. So the density is going to increase. So, so as those particles become closer and closer, the density is going to increase, okay? And then explain in terms of motion of molecules. So the more that they gain energy, the more chance of collision. So so when you compress a gas, the particles become closer and closer and closer. And because of that, temperature rises and they get more excited, so there's more chance of collision. So that's 4 marks there for kind of saying one thing, which is good really, because 3 marks by year. We run into some problems, and I think of the 3 teachers that tried this, we all assumed something which wasn't. So I know when it comes to pressure, we're taught to use the equation PV over T equals the constant, and because it's a constant, we can even do this, and you could be tempted to, you know, just ignore the pressure because, you know, we haven't got any pressures here. So I would have put 10 degrees Celsius as, and I probably would have converted that to kelvins and said 10 degrees Celsius. And then this would have been 60 degrees Celsius. And if you do that, you do come out with the same similar answer. But there's a much easier way to do it, because we need to recognize that this, again, is another gradient question, Remember that y equals mx plus c that we used earlier in the paper. It kind of relates a little to that. So we're going to do the change in y over change in x to get the gradient. So the change in y is 23 minus 19.5. So that's because the temperature was on the y-axis. The change in x is your temperature on the bottom, 60 minus 10. That comes out to 0.07. And what that tells us is that for every centimetre cubed, or sorry, I should say, because I even wrote it down, for every 1 degree Celsius, it's going to either increase or decrease, depending on which way, whether you heat it or cool it. It's going to increase the volume by 0.07 centimeters cubed. That's what that means. Now that we know that, because we need to take it back to when the trapped air is 0. So I'm going to pick a volume on the chart, and I've picked 19.5. Well, or I'm going to choose one of these volumes. I could have chosen 23 centimeters, but I've chosen 19.5 because it's almost quicker to get to 0 then. And I want to see how many times this rate of change, goes into that volume. And that's going to give me that temperature of 278.6. Bear with me. So, because I started at 19.5 centimeters cubed, which was at 10 degrees Celsius, I need to now take that from the 10 degrees Celsius, which is going to be minus 268.6 degrees Celsius. For 3 marks, that is a really, really hard question. And if you've got that without watching this video, you should be really, really proud of yourselves, because it is a hard question to interpret. Not many of these come up, therefore we haven't had practice with these. This is total problem solving. And then a nice easy one then. For 1 mark, state the name given to the temperature when the volume is 0. Absolute 0. That's all it is. So, you know, for 1 mark there, we got that. For 3 marks, we've got all that. Okay? If you're still struggling with this, come and see me. I'll do my best to go through this with you, but it will make sense. And again, you're probably going to pick up marks if you try to use this. If you use this, you would have seen that these, when you plug the numbers in, you're going to come out with around about 0.07 for each side, and that might get you a mark. So you're trying something. But really for this one, it's realizing that the gradient, and once you've got the gradient, you can extrapolate back to 0 if you start at 10 degrees Celsius, which was 19.5 volume. Okay, I'm going to stop it there. Well done for getting through all this. It hasn't been a short video, but these triple papers tend to be quite lengthy. Okay, thanks for watching.